All right, let's talk about something we've all felt. You're using an app, you tap something, and you wait. Then you use another app, and everything is just instant. What's the deal? Well, a lot of the time, the secret isn't some superpowered server. It's about being smart with data. And today, we're pulling back the curtain on one of the biggest secrets to database performance: indexing. This is what separates the apps that fly from the ones that crawl.
So, I want to start with a number that should honestly be terrifying to any developer: 100 seconds. Imagine, in a worst-case scenario, this is how long it could take to find just one single person in a table of 100 million users. 100 seconds? In the world of apps, that's not just slow, that's completely broken. So, the big question is, how on earth could a simple search take that long? Well, picture this. Imagine all your data is stored in a library with a million books, but there's no card catalog. The books are just piled up. If you need to find one specific sentence, you have no choice but to start with the first book, read it cover to cover, and if it's not there, you toss it aside and grab the next one. And you do that a million times. It's the brute force approach, and it's just painfully slow. And this brute force method, it actually has a name. It's called a full table scan. This is the villain of our story today. You see, databases don't store data in one giant continuous line. They chunk it up into what are called pages or blocks. And without any kind of guide, the database has to do the digital equivalent of reading every single page, pulling each one from the disk into its memory, just to find that one little piece of information you asked for.
And this process really shows you just how inefficient it is. Step 1, pull a page from the disk. Step 2, scan it. Step 3, not there, throw it away. Step 4, pull the next page. And you repeat this over and over and over. The most expensive thing a database can do a lot of the time is physically reading from the disk. We call that I/O. A full table scan just maxes that out completely. It's like trying to find your car in a giant parking garage by driving down every single aisle, looking in every single spot. It works eventually, but man, is it a waste of time.
So if that's the villain, how do we defeat it? Well, we bring in a hero, and that hero is called the index. The best way to think about it is exactly like the index in the back of a textbook, right? You don't read all 500 pages to find out about photosynthesis. No way. You flip to the back, you look up P, find photosynthesis, and it tells you, go to page 247. Boom, done. An index is a database's shortcut. So what is an index technically? It's really important to get this. It's not the data itself. It's a completely separate, much smaller data structure. What it does is it stores two things: a sorted copy of the column you want to search by, say a list of all the user IDs in order, and for each ID, it stores a pointer. And a pointer is just a fancy word for an address. It's the exact location, the coordinates, of where the full row of data lives on the disk. This quote just nails it perfectly. The best solution to search billions of rows is to avoid searching billions of rows. That's the whole game right there. Indexing isn't about doing the search faster, it's about doing less searching. It allows the database to look at your query and say, I can completely ignore these 990,000 pages because I know for a fact the answer isn't in there. It's about elimination. And when you compare the performance, it is just night and day. Without an index, you're doing a full scan. The search time grows in a straight line with your data. Double the rows, you double the search time. That's what we call O(n) complexity. But with an index, the search is an index seek. The performance curve is almost flat. We call this O log n. And what that really means is you can go from 1 million rows to 1 billion rows, and the search time, it barely even budges. It is an absolute game changer. Okay, so what is the magic here? How does this actually work under the hood? Well, our hero's secret power is a special kind of data structure called a B-tree. That stands for balanced tree. This is the workhorse behind almost every database index out there. And if you get how a B-tree works, you'll get how indexing works. So a B-tree is exactly what it sounds like. It's a tree structure that's always kept sorted and balanced. A search always starts at the very top, at what's called the root node. Think of this node as a really high-level signpost. You're looking for user ID 51, and the root might just say, anything less than 100, go left. Anything more than 100, go right. In one shot, you've just thrown away half the entire tree. So you follow that pointer down to the next level, to an intermediate node, and it does the exact same thing, just more specific. It might say, okay, for things between 1 and 100, if it's less than 50, go left. If it's between 50 and 75, go right.
See what's happening? With every single jump down the tree, you are zeroing in closer and closer to your target.
And then, in just a handful of these jumps, and I mean just a few, even for a massive table, you hit the bottom. You arrive at a leaf node. This is the end of the line for the index. And this leaf node has exactly what we need. It has the value you were looking for, and right next to it, that magic pointer, the physical disk address. It tells the database engine, hey, the data you want is on this exact page in this exact spot. No more searching needed. It just jumps right to it.
Okay, so we've got the B-tree engine, but how does it connect to the actual table data? Well, that's where things get interesting, because indexes really come in two main flavors, clustered and non-clustered. They both use B-trees, but they handle the table data in completely different ways.
And honestly, the analogies here are the absolute best way to get it. A clustered index is the table's physical order. Think of a dictionary. The words themselves, the data, are sorted alphabetically. You can only have one physical order, so you can only have one clustered index per table. A non-clustered index, on the other hand, is that separate structure we've been talking about. It's like the index at the back of the book. It's a separate list that points to the page where the data lives. And since they're separate, you can have a bunch of them.
And this is so important that databases just do it for you by default. When you create a table and you say, this column is the primary key, like a unique user ID, the database automatically builds a clustered index on it. That means the entire table is now physically sorted on the disk by that user ID, which is why looking up users by their ID is almost always lightning fast.
Now, B-trees are amazing, they're the standard for a reason, but sometimes you've really specific problems that need a specialized tool. B-trees are awesome for searching on one-dimensional data like numbers or names. But what about, say, a map?
Yeah, think about it. When you open up Uber or Yelp and it says, find restaurants near me, that's not a B-tree, that's a geospatial index, which is built to handle two-dimensional latitude and longitude data. Or when you type something into a search bar on Google or any website, you're using what's called an inverted index. It's a structure that maps words to all the documents they appear in. It's all about picking the right tool for the job.
Okay, so at this point, you might be thinking, this is magic. I should just put an index on every single column in my table? And whoa, hold on. As with pretty much everything in tech, there is no free lunch. Indexes give you incredible speed, but they come at a cost. And this is the big one, the fundamental trade-off. Indexes make your reads, your select queries, way, way faster. But they make your writes, your inserts, updates, and deletes slower. Why? Well, think about it. Every time you add a new row to the table, you don't just write the data once. You also have to go and update every single index on that table to include the new entry. So you have to be really strategic. First off, indexes take up space on your desk. Sometimes a lot of space. But more importantly, there's that write overhead. Let's say you have a table with, 10 different indexes on it. When you run one simple insert statement, the database is actually doing 11 writes behind the scenes, one for the table itself, and then one for each of those 10 indexes. On a table that gets a lot of writes, that can absolutely crush your performance.
Which really brings us to the key takeaway. Indexing is, without a doubt, one of the most powerful tools you have for making things fast. But it's a precision tool, not a sledgehammer. The goal is never to just add indexes everywhere. The goal is to add the right indexes, the ones that support your most important queries without slowing everything else down. So the question you should always be asking yourself isn't just, can I make this faster with an index? It's, are my indexes actually helping, or are they starting to hurt?